So good morning, everyone. Thanks for having me here in Munich. It's a long way to travel, but you've got some nice weather, so that's always a plus. It's winter in New Zealand at the moment. So hands up if you've heard about Xero before. One person, two people. Yeah, I didn't think so. Being based in New Zealand means that we're not worldwide known at the moment. But what we are is an accounting software firm. Okay, and we're cloud-based accounting. We're only about 10 years old as a firm, so it's quite new as a software company. And we market ourselves as beautiful accounting software, right? So it's very design-led as software. The catch is that for many years what we've done is just record what people have done in their accounting packages and just report it back to them, right? And so we've been focusing now on doing some more interesting things with this software in terms of machine learning. Now, the software is designed for small businesses, so if you're a plumber or an electrician or you run a cafe or a hairdresser, those are the types of clients that we kind of expect. We're actually quite a big firm, so by New Zealand standards, we've got 1,600 people, and there's 12 offices around the world. So we're mostly in English-based countries, so we started in New Zealand. We've got about 200,000 customers in New Zealand, 400,000 in Australia, about 200,000 in the UK, and I think it's coming up to 100,000 in the US as well. So we've got 1 million subscribers as of about a month ago, and we've added 500,000 just in the last 2 years. So we're increasing in size quite quickly as a company. We store quite a lot of data. As far as accounting software goes, I realize in big data terms, having 3 petabytes of data is not huge, but it is actually quite a lot from an accounting perspective. And we process a lot of transactions. So most of the software that people would interact with in terms of entering bills or creating invoices, we also have bank feed transactions coming in. So you get both sides of the accounting equation come in, and people can reconcile those transactions. In the month of March, we had 220 million transactions coming through, so quite a decent volume. And as I mentioned before, what we've traditionally done is just report back what people have entered. And what we've realised is that we've been collecting a lot of data for a lot of time, and we should start using that to offer more interesting suggestions to people. And it's nice structured data, so it's all in relational databases. We use Microsoft SQL Server behind the scenes, so it makes it very easy to do machine learning on it. And what do I mean by machine learning? So in its most simplest sense, it is literally just an algorithm plus some data producing a model. If we took the algorithm away and replaced it with a person, it would just be statistics. If we took the data away and just had the algorithm, it would just be a heuristic, so a rule that you're creating about the world. The kind of data that we're dealing with is what you find in spreadsheets. So this is an example of a very famous data set called the Iris data set. It's about flowers. There's 150 rows with measurements of flowers. 4 of the columns, which we would call features, describe things about those flowers, like the petal width and petal length. And then you have a target, which is just a type of flower. And there happens to be 3 types of flower in this particular data set. They're numbered up here, 0, 1, and 2, but they're types of the iris flower. If we were to visualize that data set, this is what it would look like. And what we see is that in some dimensions, the blue set, which is the iris setosa flower, is completely separable from the rest. So from a machine learning perspective, this is quite an easy data set to work with because at least one of those targets is quite separable from the rest. Whereas the other 2, the green and the red, are mixed up, so it's a little bit harder. And the kind of model that we might produce from this, a very simple model, is just a decision tree where it's got one rule at the top and it's broken it down on petal width, splitting it off into different sorts of flowers. So this is kind of an example of classification. So we're predicting a category or a type of flower in this case. And an alternative might be regression. And these are all examples of supervised machine learning. So this is a simplified view of the machine learning world. And so we're down over here in the supervised set. So most of the stuff that we do in accounting is supervised. We've got the target that we're aiming for. It might be a number, it might be a category, but we've usually got that labeled data, which is quite nice. Now, when you're dealing with machine learning from a business sense, which I've done in many different industries, it usually always starts the same way, that you have a business problem that you think you want to solve in a smarter way. And you have the question of whether machine learning can actually solve that problem for you. So you start down this side of the flowchart, where you have that business problem and you're asking that question, and then you engage in usually some data science. And the bit that I've just shown you so far is just the little red circle. It's just the measuring of the accuracy. The data set's been given to us. We pick an algorithm, we go with it, and we produce a model out of that. But actually, a lot of the work goes into collecting the data. And Xero's been doing that for 10 years with collecting everyone's accounting information. So we've got a lot of data sitting behind the scenes, but the time is spent in doing the feature engineering on the data science side. Now, often if you don't have the data science piece work out, all right, so you can't actually produce a model that will work, you might find that you have to redesign your system, and a lot of people don't think about doing that. So working in agriculture, we had a problem where we had half a dozen people spend 2 months working out where trucks would go. Right? So farmers would say, I want my farm to be serviced by a truck, and these people would take all the farmers' bids for the year and spend 2 months working through where the trucks would go. And when it came time for the trucks to go out to the farms, if that time didn't work for your farm anymore, tough, you would miss out for the year. And so we asked the question, could machine learning route those trucks in a more efficient way so those people didn't have to sit there and do it for us? And it turned out that we couldn't do it in a way that was efficient enough compared to the original system. And what worked a lot better was actually just booking it like a movie theatre. So farmers would go in and say, here are some days that the trucks are available. They would book that time, gave them a sense of control. No one actually had to work out where the trucks would go on a given day because the farmers were doing that for them, and it meant the system was far more efficient. So there are plenty of examples where machine learning doesn't work, and it's actually better to redesign what you're doing. So assuming that you got data science working properly, so this whole little circle there, and you proved that you could solve a problem, there's still this other half of productionizing that system, of how do you get it out to the customers. And there's usually a lot of things around pipelines, how are you getting the data to the systems that you're training, how are you going to train those models, when do you choose to train them, and when do you choose to use the ones that you've trained new rather than the old ones. Then you've got to make predictions on that data. You've got to test that it's actually working all the time. It would be problematic if you replaced a model, new model, with something that was worse than the model that you had before. And how do you track that? And then you often have to make changes to your user interface if it's something that you're making go away. And then, of course, it goes into live, and there's often bugs that you find in other pieces of the software have nothing to do with the machine learning, but come out of doing that. So what I'd like to take you through today is a couple of examples of how we've used machine learning, and we'll go through this whole diagram of what we were thinking of. And the first bit is what we call account code suggestion. So in accounting, what you have is a chart of accounts. So when any transaction is made, it's coded to a particular account. And all those things are is just buckets which describe how that money has been spent. And they're used from an accounting purpose to do things like calculate how much tax you owe, how much money the company has made. So it's kind of important that you get the right bucket of money when you're coding these accounts. And about this time last year, the team that was working on this invoicing screen, so producing an invoice for a customer, had the opportunity to embed some machine learning. And they weren't experts in the field. They'd done a machine learning course online and decided that they wanted to try it out in the software, and were given permission to do so by their managers, which I think was quite forward thinking for the company at the time. So what we see on this invoicing screen is we have this nice account that I've circled there, which as the person has typed the line of what they're selling, in this case it's golf balls, they've coded it to a sales account, right? So the person writing this invoice has to know that that goes into the sales account, which as a small business owner, if you're someone in retail, for example, you might not know how to code this kind of thing. So often your accountant might have to come along later and fix these kind of things. So we thought it would be nice if we could make that box go away. So actually taking the process of accounting, of coding things to accounts, away. So from this page, these are the kind of things that we might see as features, bits of information that we could use for machine learning. It turns out that a lot of them aren't actually useful because they never change. So for example, when you're typing an invoice, you're going to potentially type it to a different person each time. You're typing a different line item, a description of what you're doing, the amount that it's worth, the position that it is if you've got several items on the page. But things like the country that you're operating in, we find that it's something like 99.9% of them are the same country. So it's not a valuable thing to have as part of that learning system. And things like the number of accounts you have in the system when you're writing an invoice, that doesn't strictly change a lot. So what we do with this is turn these into features so that the machine can understand it. And machines don't understand categories very well, so we turn it into numbers. So categories like the user who's entering this in, the supplier or the person that we're selling this thing to, get one hot encoded. And what that means is that we turn a column of category values into one column for each category value, and the values in those new columns are just a 1 or a 0, depending on whether they're there or not, right? So in the flower example, there are 3 sorts of flowers, which mean I end up with 3 columns, and the columns are just a yes, no as to whether it's that type of flower or not. And this is something that the machine can understand better than that category list of flowers. So in the machine learning world, if we were picking an algorithm to work with in our simplified view, the kind of things that Xero is interested in as algorithms fit into that big blue bubble. There isn't a lot on the unsupervised side, a little bit, but it's not huge. And in fact, most of the stuff fits into the classification set, which is what we're looking at here. We're trying to predict a category, which account code that they're going to use for a given line item on an invoice. Now, when we come to measuring accuracy, it turns out there's a bit of a trap with doing this for accounts. So usually in machine learning, you have a training set and a testing set. And you break your data up into those sets, and the things that are in the testing set are never seen in the training set. And in fact, what we normally do is a thing called cross-validation. So we randomly put rows into folds, and each of those folds contains a unique set of rows that is not in any of the other folds. So all the information is in one of those. So this is 5-fold cross-validation. There are 5 buckets of information. The rows are randomly in each of those. And when we come to produce a training and test set, we take one of those folds out and place it in the test set and leave the rest in the training set so that everything is unique to being trained and then being tested. So we're not seeing the rows that we're testing on at training time. And then we'd repeat it for each fold of the data. So step 2, we take fold 1 and put it back, and then take fold 2 out, and that becomes our testing set. So as a result, we get to test with everything that's in the training set, and it's never been seen before when it is tested on. But if we were to do this with our invoices, and we have invoices, time is important, right? So if we randomly selected rows, we'd end up with rows in the future that would end up potentially in our training set. So our testing set would be testing on things that haven't, the training set has seen things after those things, which doesn't happen in practice, right? Because as you're entering in invoice lines, you're going to have new things come along, and you're not going to know what the future is. That's the whole point. So what we do around this is to test how good our machine learning algorithms are. We take the first invoice line that we've ever seen, and we place that in our training set. And then we take the second invoice line, and that becomes our test set. And then the next step, so this would be the next fold of cross-validation effectively, we take the second invoice line and place that into the training set and just take invoice number 3 and place it into the test set. And it means we're only testing on one thing at a time, but it also means that we're never selecting rows in the future as part of that training set. So we'll step through it there. And then when we come to compare the algorithms, we've got the machine learning algorithms that we might be wanting to test with, as well as simple rules like what is the most frequent account code that they've used in the past. So our team thought that they could author some rules, some heuristics that were better than the machine learning algorithms because they've been working on invoicing for quite some time and they thought it was quite a simple problem. So if they just selected the most frequent code, then probably they'd be better than the machine. And then we also have defaults from the chart of accounts. So when people select an account, they might say, I expect when I'm writing an invoice, the default is always going to be this one account. So that's an option as well. And what we found when we did this across accuracy is that those defaults, and there's 3 different defaults that they can use, are the bottom 3 lines in terms of accuracy from this graph. Right, so they weren't very good, topping out at about 40% accuracy across 2,000 different organisations with many different repeats of that invoicing cross-validation kind of process. The next 3 lines that you see are the rules that the team created. So they're the most frequent code, the last used code that the person had. And the top couple of rows are machine learning algorithms. So they basically trounced all the rest, which was quite positive and kind of reinforced the fact that we should be using machine learning to solve this problem. We wanted to see how quickly the machine learning algorithms did better. And what we found is after the first invoice line, the machine learning algorithm was better, right? So we may as well use that. Then there's a catch. So what do we do if we don't have any history? So the machine has nothing to learn from. So there's a couple of strategies that you can take. The most simplest of these is the one on your left, which is, this is a do-nothing machine, that picture, so it just goes around in circles and does nothing. So you don't offer any suggestion in that sense. If you have a little bit more information, so for example, people when they write a chart of accounts, there's a default set that they could use. So we could look at people using the default set of accounts and use that to make a prediction towards a particular customer's set. So everyone has potentially a custom set of accounts. That's what's unique about this problem. There's not one set of accounts that everybody uses. Everyone has their own set. So the wisdom of crowds bit is actually a little bit hard, but that's the strategy that you find as an alternative where you might offer a suggestion, but it potentially might not be very good. So it turns out that at the moment what we're using is the do-nothing approach. So we're not offering any suggestion. If we don't have any history from that person, if we, what we're working on at the moment is towards that wisdom of crowds bit, but it turns out to be quite hard. So trying to learn from everybody else's data and make a prediction about an account. So we also did some work testing the different machine learning algorithms. I know it's hard to read on these slides, but the first set that we used, because the team weren't familiar with machine learning, was just logistic regression and naive Bayes, which are not especially advanced machine learning algorithms. So as an alternative, we tested a bunch of other ones and optimized the parameters on them. And as it turns out, the logistic regression that they used in the first sense was actually the best one, so they got lucky. And what you don't see in this is that they're all just about on top of each other with the score, so there's very little difference in the average result in accuracy. So of all the set that we could use in machine learning, what we're actually doing is just logistic regression. Very simple approach, but it tends to work. And now all I've shown you is just that data science bit, right? And it took the team about a month to come up with a solution that they found worked for this particular problem. The other half of it took almost a year. Right? So doing the productionization of actually getting the system out for customers to use took a lot longer. And that was because we didn't have any systems in place to send the data to the models, and we had to do all that from scratch. There was lots of things to think about of when do we retrain. We've got 1 million customers, we've got to retrain 1 million models because each chart of accounts is different. So we have to train a model for each customer. When we've trained it, how do we get the prediction back to the interface? And making all the changes to the user interface in order to do that. And what we found is basically productionization is really hard, right? And it's something to be aware of if you're getting into machine learning. That is the hard bit. The machine learning bit is often the easier part from a commercial company sense, right? So what we ended up with is an architecture. This is a very simplified view of it. We do everything in the cloud, so it's all Amazon AWS services. Basically, we have an API you see in here called Elicit that puts all of our customers onto a training queue. It does this every 24 hours, so the models are refreshed every 24 hours. We're working on ways to be smarter about that because it doesn't make sense to retrain the models if nothing has changed. We have a fleet of containers that operate on our databases. So our databases are split up into shards across different regions. And there's only, I think, about 10,000 organizations in each shard, so we have a lot of different shards. So the fleet will go to the appropriate shard for that organization, get all the data it needs to train the model, and then place it in a model store up the top. We started off using S3 as the model store. We found that was too slow. So we're actually using Redis for that. The models are quite small, so we're only training, I think, on the last 100 invoice lines. So that's not a huge amount of data to learn from, and can be quite quick. When we come to predict, we have a Lambda function that does the predict. So it goes away to the Redis store, grabs the model, does a predict on that, and then returns it back to the interface. We also have a back end that's, I think this is Datadog's dashboard. So we send a whole lot of analytics through so we can track in real time what the performance is. So we're operating on about 90% accuracy. So that means about 10% of the time when we make a suggestion, people are changing that suggestion. It turns out that something like 65% of people have more than 95% accuracy. So we're very accurate for a large number of our customers, which is quite cool. There are a few that are not very accurate at all. And it turns out to be because they have a lot of accounts that they use, and so we don't see enough history to make a good suggestion for those people. And the invoicing screen, so remember how I said they were redesigning that invoicing screen. This is what our new invoicing screen looks like. And we've made the account, it's hard to see here, it's just there, go away, so it's not something people have to enter anymore. We make that suggestion while they're typing the line on the invoice. And then they can have the option of changing it if we don't get it right. So that took us a year to do that, and that was our first one that got released as a machine learning project probably a couple of months ago now. So it's gone out, I believe, to about 100,000 of our 1 million customers. We found a whole lot of bugs in the interface as the process of doing this. It had nothing to do with the machine learning at all, but when people see a change like that in their interface, they consider it's the machine learning that's got the problem, and it turns out that it wasn't. So we've been quite cautious about releasing to all of the customers so they don't get a bad experience out of that. So the second thing that I'd like to show you is report code suggestion, which is, it sounds like a similar problem, but it's actually quite different. So in your chart of accounts, so this is the same chart of accounts screen, we have a thing called reporting codes, which are these codes here. They're broken down into hierarchical codes that can go several levels deep. They're 3-letter codes. And what these codes are used for is accountants will use them for reporting purposes. That's why they're called reporting codes. So when they're producing a report that says how much cash flow has the business got, they can press a button and it will automatically produce that based on the accounts that they've got in the correct coding system. Now, what's different about this is that everyone has the same potential set of reporting codes. right? So it's not the case that everyone's codes are different. These are codes that Xero has specified as available. So it means that we can build one model for everyone, which is quite different. Just to give you an idea of how hierarchical these sets are, so we've got an example here that's employee pay entitlements. So there's 4 blocks to the code. If you were selecting it into the interface, it's actually quite a hard thing to select. You have to scroll down, open out each of these drop-downs, and select the code. And a lot of people just get tired of doing it halfway through, so they'll select a higher level code than what they perhaps should. And it's very time consuming as a process. So usually an accountant would go through and settle these codes. If you've got 100 different accounts in your chart of accounts and that accountant has 10 different clients, then there's 1,000 different reporting codes that you have to go through and manually set for each of them, which is not very good at all as a user interface. So again, this was something that we thought we could make go away in the interface, that people don't have to select. It turns out we don't have as much to learn from. We really just have the account name and the description, which we break down into features. So we have text, which we break down into words and then turn into columns. So we have 1 column for each word. But the catch is that there's 10,000 words in the set. And we're only operating in English, right? So if we have other languages put into that, there's quite a lot of words, which end up being quite a lot of columns, which is really too much. So we reduced that down to 500 words. 500 was picked because that's the number of words that repeat more than once in that training set. We're not doing anything fancy with something like principal component analysis to reduce down that set. We are just doing a very simple count of those words. There's other problems around what people type because it's free text that they can type. There can be lots of different case for the letters, so you can have capital letters and lowercase letters mixed up. We just turn everything into lowercase. We don't worry about capitalization. There can be names of things. So if it's a name of a company, then that might be meaningful things to learn. But if it's something like John's account, that might be meaningless. We don't do any selection on those names. If they happen to appear in the set of things that happen more than once, then they'll end up in that training set. There also turned out to be a lot of spelling mistakes, which sort of surprised me. And then I thought about it and realised that a lot of small business owners perhaps aren't necessarily as literate as you might expect, and they're just typing things for them. They're not expecting anybody else to see it. So there's no reason for them to have correct spelling. So that turns out to be a bit of a problem when you're categorising things and they're spelt wrong, right? Because there might only be one example of the thing that's spelt wrong, and you'll make a wrong decision about that. So after correcting for spelling, we can actually lift the accuracy by 1%. So it's worth doing on this set. If we look at 1 million different accounts, so these are randomly selected across a bunch of different organisations. I think they're all New Zealand-based organisations in this graph. We tried a few different algorithms. So naive Bayes performs very poorly on this data set. We had a product called Work Papers, which is an add-on to the accounting engine, which does some default kind of rules. So it says things like if you have the word car or vehicle, then we put that to perhaps vehicle maintenance as a reporting code. So someone has gone through and gone, these words mean these reporting codes. And it's the longest if-then statement that I've ever seen. It's quite substantial. And it doesn't go very deep either, so it only goes to a couple levels of the code. So you can get up to, I think, about 6 levels deep, and it only goes to 1 or 2. And I would say that's partly because it's an if statement and they don't want to be bothered doing it for all the different cases. But it turns out we only get about 30% accuracy out of that. So we tried logistic regression on this problem. It takes a very long time because there's 500 columns and 1,000 rows to work from. And we found that it got about 80% accuracy, just a little bit less than 80%, depending on the region. So we ended up regionalising the model. So we have one for Australia and one for New Zealand. despite being neighbours, we use quite different language on a few things. So we found that putting it into regions worked better. We also tried random forests, which worked the best. It can get up to about 85% accuracy on a random forest, but it turns out to be very, very slow. And that's because the trees end up being huge. And you don't want to use a lot of trees because then the models blow out in size. So as an example here, this kind of problem being trained would result in a model that's 2 gigabytes in size for 50 trees, which is just horrendously huge. The kind of predictions that we might make, so these are some examples of codes. I've only shown you the ones the system got wrong because it's not interesting when it's right. So here's an example where it's an expense, it's a cost, and it's a purchase. What it's predicted is a repair. It turns out the name that was on this account was warehouse repairs. So it makes sort of sense that it said that it's a repair. It's possibly the right code to be using in this sense. In some examples, the machine was less specific than what the humans had coded in that case. And that might be an artifact of people not bothering to select all the way down in the codes because the machine can only learn from what it's seen before. So if the majority of people have selected a higher level code rather than going down further in the levels, that's what it will predict. This next one is office furniture, and it hasn't got the furniture bit on the code. So again, that's an example where it's been less specific than it needed to. And this final one, where it says that the person has coded it as a current liability, the predicted thing was a bank account as an asset, which confused me as to why it got it so wrong. I sat down with an accountant to figure that out. The name on the account was BNZ, which is a bank in New Zealand. So it sounds okay that it's a bank account. The account type for this was set as an asset. So again, that seemed to make sense. And what the accountant told me is it's probably a mortgage, so it's a liability. And for some reporting purposes, they might want to see it as a liability. On certain reports, they might also want to see it as an asset. So it's actually a choice thing that it's ended up being this way. And so the machine hasn't quite wrong, but it's not right either. It's just one of those strange things that we probably couldn't get right. If they'd entered more like the word mortgage in there, it might have actually predicted it as a liability. So we ended up also looking at neural networks for this, because 2 gigabytes as a model size is just massive. And the nice thing about neural networks is that you only need to store the weights, and so it ends up being potentially quite small. So we have about 550 inputs. These are all our columns with our numeric values. And there's about 200 different reporting codes that they need to output. That's why the trees are so big, right? Because there's 200 different options that they can end up with. The middle layer that we've got, so this is just a very simple neural network, has 370 nodes roughly. The way we came to that number was using a rule of thumb with machine learning that you take the number of inputs and add them to the number of outputs, which gives us about 750, and then divide by 2. It actually tends to work a lot better than you'd think. We did optimize around that number, and it turns out that it was slightly higher than the halfway point, but not far off. So there are other strategies that you can use for neural networks around selecting that middle layer and adding in other layers, but this simple strategy worked very well for us. We train everything in Amazon. So it takes about 5 minutes to train 1 million rows for this particular problem, and end up with an accuracy that's about 90%. So a little bit higher than those random forests, which is quite neat. And, oh, my clicker has died. No, laptop has died. I will let technical services fix that. Yep, sweet. Okay. Thank you. Sometimes it just needs someone else to look at it, right? Okay, so of our model, so the model accuracy was comparable, roughly, with the random forest. The training time was about the same in the cloud. You can parallelize random forest really well, so it can be quite fast. But it turns out the model size, as we talked about, with the random forest was 2 gigabytes in size. The neural network's 20 megabytes. So that's obviously the more favorable model, especially given that everything else is the same as a system. So again, that's just the data science bit, right? And so for your interest's sake, we were using Keras and TensorFlow to do the neural network model. All the rest of the models that you've seen are from scikit-learn, so Python. When we came to do this, we're still doing this. So we solved the report code bit a couple of months ago now. It's not as hard with the data pipelines because we can train a model offline, right? That we can do an extract on a lot of rows and train the model. We don't have to retrain it. Those report codes aren't changing all the time. So we can train once. We don't have to think about retraining that, which is convenient. The framework that we had in place for doing the prediction doesn't work in that sense of pulling out models and going through that. So what we're getting to at the moment is a model that's loaded into a container. We have multiple containers that can be routed to that all running the same sorts of models. Each container will have all the regions models because 20 megabytes is quite small and we've only got half a dozen regions to look at the moment. So it just moves to the right region, makes a prediction on that and returns it back. So it's actually a very simplified architecture compared to the previous one. There is a catch around encryption that also makes it hard. So a lot of these models will naturally encode what people have entered. And we're very careful about customer privacy. So none of the work that we do is ever on our laptops or our desktop machines. It's all done in the cloud. And we encrypt everything that we're working on. So when we do an extract, we encrypt that extract and write it to an encrypted bucket. We also encrypt all the models. So that's something that we have to work through for this one. It doesn't encode the same kind of user information because it's just account names and descriptions. It's not what they're selling and how much those things cost. But it's still something that we have to think about here. So we're still working on that. So I wanted to leave you with some final thoughts because I might have given you the impression that machine learning is quite easy because the examples that we've got in accounting are quite straightforward from a spreadsheet sort of point of view. But it turns out it kind of depends. So we've picked examples that we know a human can do, right? And if you're starting with machine learning, if you have a problem that you think a human can code, given the same information, so if I gave a human a spreadsheet and said, tell me what sort of flower I'm predicting, or tell me what account code that this transaction belongs to, there's a good chance a human could do it with a degree of accuracy, with that, only that information. If you give a machine that same information and you can prove that a human can do it, there's a good chance that that will actually work. So it's easy from a machine learning perspective. There are plenty of problems that are very hard from a machine learning perspective as well, but we didn't start with those. We started with the easy ones. Turns out there's a lot of data cleaning. So most of the time with the report code model was spent on spell checking and getting that fast enough to do it in real time so that when we get an account name and description come through, that we are actually able to spell check it and have it come up in the interface within milliseconds as opposed to going through a dictionary and checking for the right word. We just take the closest hit, that kind of thing. And productionization is really hard, right? It takes a long time. It's by far the hardest part of that process. And I've done certainly a lot of technically challenging machine learning problems in the past where you're creating new models that haven't, like new algorithms that haven't been made before, but absolving yourself from doing any of the productionization piece. Here, when you're doing something for industry and you have to productionize that system, it takes a long time to think about that, and often the systems that we have in place for what the system was designed for, so we were accounting software that were reporting things, we weren't thinking about making suggestions, right? So we have to re-engineer some of our back end to support that, and that takes a really long time. So yes, that is all I had. Are there any questions?
Yeah, thank you very much. If there are any questions, please give me 1 second. I will come to you with the microphone.
I'm one of those
Just wait.
Oh, sorry. Yeah. I'm one of those small enterprise owners, and what I would really like to have would be putting all my documents into a scanner, yeah, and run a batch, and then have your software book it. How are the chances in the near future that you're going to achieve that?
So we are a publicly listed company, and I can't really talk a lot about what we're doing, but it's reasonable to assume we're working on that.
Are there more questions?
It may be a bit of a naive question, but once you've reached productionalizing your ML, will it ever be switched off again, or is it clear that it is part of the ecosystem which is there to stay forever?
So when we first started, we wondered about how we're going to measure whether people like the system or not. And we decided it was going to come down to customer tickets. So when they basically put a complaint in to Xero and said, we don't like using this software. When we had the first 10,000 customers using the software, we didn't have any tickets that were take away the account suggestion. It was, we found this bug that this thing doesn't work as we expected. And it was because they'd seen something new around the machine learning. It wasn't the machine learning that was at fault for that. Since we've gone out to 100,000 customers, we've had, I think, 2 tickets, right? And both of those people said either we've made the wrong suggestion or they like to choose. So they actually want to be choosing the account. Just because we're a customer-facing company, we've actually thought about, could we turn it off for those customers? So there's a switch behind the scenes that, yes, we could turn it off for those customers, but could we give them the power to do that themselves? For those particular ones, it turns out they're quite unique in the way that they deal with their accounting packages. So they have a lot of different accounts that they're selecting from, so it was more likely that they were going to be wrong. We are going through the process of working out how we can make those models more right as well, so that they won't have as many mistakes come up. And they're only, I think they were down at 60% accuracy, so it wasn't terrible, but obviously if you're doing a lot of lines, if you've got 100 lines on your invoice, 40 lines that are wrong is a problem. I think for now we've turned those 2 customers off, so they're not getting the suggestions, but the plan is to make a change to their user interface so that they can choose whether to get them or not. Given there's only been 2 complaints, I don't see it being turned off for a lot of things. The report code one is actually an interesting one because we can actually make the suggestions without needing to have a user interface change because there's a thing called draft reporting codes. So we would offer a suggestion that would sit in draft, and when they accept that suggestion, it goes through and is used as a reporting code. We can do all that behind the scenes. It's not going to really affect the user, so it's not something we would seek to turn off. And the feedback from the accountants has been that if we can do it with 90% accuracy, it's more than good enough, especially since the ones we're getting wrong are right at the highest level. So if you just took the very first block of code, it's something like 99% accurate. So they're comfortable enough with that kind of inaccuracy once it gets down to all the different levels. Sorry, that was a very long-winded way of saying, but no, we're not turning it off.
Are there any more questions? Okay.
Okay, so that's maybe a little bit of a technical question. On the slide where you showed your neural network, we could see the target labels there, but you said before that they are very hierarchical.
So we flatten them out.
Yeah, but why not have that hierarchy explicit there? Because it's useful, I think.
So yes, you're right. We did think about that. Given the accuracy on the flat codes, we were pretty confident that that was a good approach to it. With the hierarchical codes, it does cause a bit more of a challenge in the sense of you almost want a model for each level of the hierarchy, and then you're making a decision whether to go into the next level or not, which is a little bit more complicated to think about. Again, we've gone for the simplistic approach, pretty happy with the initial accuracy, and if it became a problem to go down to those other levels, we might seek to change that. But for now, we've got something that we're happy works.
On the first example, I think it was the invoices. You said that you only predict on the basis of 100 entries.
Yes.
So is this for prediction reasons? Does the prediction get better, or is it for economic reason?
It's for speed reasons. Okay. So if a person has a lot of different invoices, it doesn't increase the accuracy a lot to add more invoice lines into that total. So there are examples, as I said, where people might enter a lot of different codes. And so for those people, we might want to be training with a larger set. I think we were initially using 50 lines on the invoice, so it wasn't a very big set at all. The thing about small businesses is that for invoices, at least, they don't have very many accounts that they would choose from. It would typically be 2 or 3. In fact, I think most have 1 that they would have, which is why the most frequent kind of works, or the last use kind of works in most situations, right? For other types of transactions, so things like bills and expenses, there are a larger set of accounts and more challenges around getting the accuracy right. So whilst we're sitting at 90% accuracy across, as an average across all of our customers for invoices, it's much lower than that for bills with the 100 invoice lines, so equivalent. So there are things that we need to change to make it more accurate, which include that optimizing that number for different customers. We had one down the front here.
More questions.
So you said you dive into the problem and try to understand this special case where the prediction wasn't right or wrong. Is there a generic way to do this, or is this always a special use case to make it understand? And is there kind of rule of thumb how to understand if the model works right or not on this case?
So we're using what the customer selected as the account to test the accuracy, right? So that is, they don't always agree with themselves. So sometimes what they select is actually wrong. So one of the things that we're doing as part of that first time thing, so making a suggestion from the default set of accounts, is using a mechanical Turk system where we will give an invoice line and a potential set from the default set to a mechanical Turk and say, code this for us, and see how well humans can do. Because the thing we don't know is just how much they agree with themselves. And if you do that with enough people, you could see that this is the accuracy we might expect from a human, and a machine is better or worse than that. It does depend a lot on the problem. So, for example, working in agriculture, we were doing things like predicting how fat or thin a cow was. And what's right in that scenario is actually different because it is subjective, but it was a score on sort of a 1 to 10 scale. And so what you considered right was area around what the people selected because, again, they don't agree with themselves, so there's a degree of inaccuracy there. So it does depend on the problem. There's not a gold standard way of doing that. But human samples is a good way to measure a baseline of how good that machine is doing.
Where was the question?
Did you look at the log probabilities of your failure modes, or ask differently, if your network, for example, is quite uncertain because it might say, I think 50% it might be this one, or 50% it might be that one. Did you think about allowing for like a top 2 or top 3 suggestion? Because this could rule out cases, the failure modes that you show, for example.
Yes, so we are now storing the confidence as part of that dashboard because, again, as I said, the people who had done the problem initially weren't experts in machine learning, so they hadn't thought about a lot of those things, about looking at the confidence of the suggestion that was being made and making a decision based on that confidence, right? We have gone for selecting the account code on behalf of the customer, so we go to the one that's the most probable in that sense. I think it would be really nice if our interface from the drop-down list presented the next couple once you selected that. That requires a lot of changes in the interface and changes in the back end to do that, so it's unlikely that it will get done in the near future. There's probably easier things that we can do that will make a bigger change to those customers. Yes, it is challenging because it is a set that you're predicting from. And so you want it to be like a search engine where it's giving you a top set of results. We're trying to take the accounting out of it, so making it, I guess, code-free or codeless accounting, so people don't have to do that step, which means we have to select the answer on their behalf rather than just give them a set of options. Cool. Maybe one last question?
Yeah, I was wondering about this very interesting rule of thumb that getting things into production is 10 times as much as the machine learning part. Because we did a lot of AI prototypes, and I would say the trend is similar, but it's just not as refined because so far the client didn't pay, so it's not in production. Do you think that this ratio is going to stay, that the getting it online part is so much more dominant in the time it needs compared to the actual artificial intelligence part, or will in the medium term or long run it turn out that getting things into production is more like an almost automated or natural step?
So I think over time it's going to become more and more easier to get things into production. So these were our first two examples, and the two engines that we've basically got as a result of that is one that can produce and deal with models for a single customer. So it's training for a single customer and looking at that person's records and producing one model for them. The other situation is one model that encapsulates everything that all of our customers has. So it's one big model or a series of big models because it's regionalized. So the architecture we've put in place covers us for those scenarios in future. So whilst there was a lot of upfront work for that, the expectation is that once we've got this report code model in place, we have a couple of other models that are actually ready to go that are waiting on that productionization pace that will slot into that same framework. So it'll be much, much faster on the second and third hits. I think the trend in cloud providers of machine learning services, so people like Amazon and Microsoft, has been to automate that productionization piece out. So you have a flow chart and you put a line in that flow chart that says, give me a REST endpoint, and then it's done, right? So there are some scenarios where it becomes much easier, and I think we'll see over time it'll be much, much quicker. But for us pioneering this kind of stuff with our software, it does take a long time.
Okay, so if you have further questions, I think the coffee break will be a perfect possibility to talk to Kathryn, to ask her. You will be available, I think?
Yep, sure.
Okay, yeah, the coffee break will start now, and the talks will restart at 11:30. Kathryn, thank you very much.